question that was asked in the previous session. The question was regarding how would a question regarding electron configuration or off-ball, principal, unschool, all that stuff, how would it really look? One of the older ways that they did the questions, and you still may see it in some way, shape, or form, is they give you 4 or 5 options with a couple of quick descriptors underneath. Another way that it could be revamped would be just to ask the question outright, and these be your A through D or E options. If I'm looking at the first question, which of the following has an electron in the excited state? First off, what does it mean that it's in the excited state? It's jumping orbitals. So it's not at the ground state, at the lowest energy level possible. It's actually above that. So if I'm looking at the examples I have here, 1 through 5, which of these would show an electron in an excited state? 2. Why 2?
Because the 2s isn't filled completely and it goes completely.
Okay. So if we're taking a look here, yeah, it's just that simple. We have to fill up the 2s before we move on to 2p. In this case, I have an electron that is moved into the 2p while I still have empty space. That tells me that electron has more energy. It's in the excited state. Same question, or actually slightly different, but same situation. Which of the following violates the off-bar principle? Which of the following examples that we see up there violates the off-bar principle? First off, what's off-bar?
Isn't it like you get to fill up the orbitals, or like, yeah, you fill up orbitals from 1 to 9?
Yep. Electrons are lazy, therefore fill up before moving into the next one. Now, this is 2 ways of asking the same exact question. All I did was change the wording of the question because the only one that's in here that violates the off-bar principle is number 2. Okay? There's only, one person put it this way, there's only so much chemical knowledge that's in the entire universe, inside the world. At a general chemistry level, what they do is they take the same concepts and they rewrite it in different ways. Look at it this way. Now what about this? And what happens is, it's actually kind of funny sometimes, there are some people who will get this one because they see off-ball and they're like, yes! And they would have missed it the other way, but the answer is exactly the same. So, last one. Wow, I did not write that how I wanted to. But, which of the following has the highest, it's supposed to be, which has the highest ionization energy? Sorry. Of these that are up here, which would have the highest ionization energy? Why 4? Chose to eat before answering. Let's see if we get somebody else to help. The correct one is 4, but why? 3. He's still trying to choose. Come on. Why would this one have the highest ionization energy? Correct. All the orbitals are completely filled. If the orbitals are completely filled, what do we know about that atom? Stable, and it's a noble gas. Okay, which one would you think would have the next highest ionization energy?
1.
Why?
Because it's full and stable.
That's correct. If we're looking at both of these, we have this one is filled and this one is filled. Technically, this would be the highest. Number 1. Why would 1? It's also closer to the nucleus. So highest, second highest. Race, second highest. What's after that? If I was just to say rank these from the highest to lowest ionization energy. We already said this is the highest, This is the second highest. Why number 3? Because the 2p orbital is halfway filled. Why not that one? Huh? Some of them are having to share. What else do we know based on which orbital we're in here? We're in the 3D orbital at this point. So why wouldn't this one qualify? Huh? Technically, good answer. What else? What do we know about a 3D orbital as opposed to a 2p orbital? The 2p orbital is much closer to the nucleus. So it's a half-filled orbital, and it's closer to the nucleus. So it's going to have that much more energy to try to remove it. Now, this leads us into where we left off last time. Oops, not that one. Not that one. That one. Brings us into our periodic trends, and we started to sort of touch on some of those as we looked at those previous questions. The big 3, ionization energy, electron affinity, and atomic radius. Ionization energy, I think, should be the most straightforward. What is ionization energy?
The energy needed to take an electron away from an atom.
Correct. The amount of energy needed, still an electron. What about electron affinity?
Energy needed to add an electron.
Sort of close. Sort of close. Not the amount of energy needed, but it's looking at the change in energy when an electron is added. So this is where we talked about, when we start talking about lattice energy a little bit, and we've added in that electron to our nonmetal, and so it drops that load of energy before it goes into the solid phase. That amount of energy that it loses by becoming stable or lower in energy would be the electron affinity. And last but not least, atomic radius, which is, I need somebody on this side. Jaden, what is atomic radius? From the electrons to the nucleus, so close yet so far. Why would that not work? The distance between the electrons and the nucleus, why wouldn't that work?
Because there's some in the closer orbital.
There's some in the lower orbitals. What also did we talk about last time about how likely we are to find the electrons at a given distance? We said that the wave function is called a what? The wave function is called a what? Or really it's a prediction of what? Math people? The chance that you'll find something?
Probability.
It's a probability distribution. The further we get out, the less likely we are to actually find it. So, a book definition would say half the distance between 2 adjacent nuclei. Put 2 of them next together, 2 nuclei of the same atom next to each other. Half the distance between the 2, because that's where the repulsion and everything sort of breaks down, would give me my radius. Now, for ionization energy, what was our trend? The part that everybody loved to give me at the beginning of the year. Up and to the left. Great. So, if I'm looking at ionization energy, we know that as we get closer and closer to our noble gases, and helium in particular, we're going to have an increase in ionization energy, or we have to put in more energy to steal things away. That makes perfect sense. Have you ever tried to steal a piece of candy or a sucker away from a little kid? They're not that fast, but somehow they keep maneuvering it around you, and you will not get it. Now, when we take a look at each of these atoms, if you hear first, second, third, however many ionization energy, what is that telling you? If I say it's the second ionization energy, an electron I'm trying to pull, or third, or fourth, or fifth, or seventh, or whatever. Now, what we notice is there's going to be a steep increase each time. So, if I'm looking at magnesium, to steal away that first electron, or my first ionization energy, 735 kilojoules per mole. When I go and try to steal the second one away, I have to put in an additional 1,445. There are questions that they love to ask about this one, especially with PES, and there'll be people who will say, oh, I only have to put in 1445 in order to ionize magnesium to 2+. No. I'm putting in 735 to get the first one, then an additional 1,445, to pull away the second. So you add those two if you ever run into that situation. Now, my next question is, why do we have such a big jump when we try to take away the third electron? We had a nice little increase. We almost doubled from the first electron to the second electron, and then we skyrocketed. Why?
Because it's in the S orbital, it's the S orbital, and then if you take away 2, you end up going back to its P orbital. And then you would have a full, stable, full, what's it called? I don't know.
Valence shell?
Yeah.
That works. So, if I'm looking at it, we know magnesium's in group 2. It has 2 valence electrons hanging out there. These are the furthest ones away from the nucleus anyway. So, as I strip those away, once I've done that, I'm left with just my p orbital, my furthest p orbital at that. It is more stable. So I have an electron configuration at that point that looks like neon. That's what I wanted in the first place. So for me to disrupt that stability, I have to put in a whole lot of energy, in order to do that. That's going to be the same with any of them. And as we said, as we move from left to right, these values for the first ionization energy and so forth are going to get much, much larger. Now, the other part where this is going to play in, moving towards big idea, at least thinking about big idea 2, is this is how we determine what type of bond is going to form. So, on which part of the periodic table would I be more likely to lose electrons in the first place? Which side of the periodic table would I be more likely to lose electrons? Left side, why? Strictly from ionization energy standpoint.
Because
That's it. We said that it increases from left to right. So that means my lowest values are going to be on the left. Which type of elements are on the left? Metals. So if I put a metal with a nonmetal to make a compound, what type of compound is most likely to result? Ionic. What about if I was to put, say, something more along the lines of aluminum with a nonmetal, say carbon? What type of compound would I think would result here? Why covalent?
The bonds are
Hmm?
The bonds are stronger.
The bonds are stronger. Why?
Because
Sure. Who's your lifeline? She said the bonds are stronger. So if I put aluminum and carbon together, she says it's going down. We got a covalent bond. Why?
Because they both have high ionization energy, so they can't, there's like transfers. We're not high ionization energies, we're like similar.
So you figure they're close together, so most likely to be similar. So most part, we're going to get a covalent bond. I like the logic. Unfortunately, what are we dealing with? Metal with nonmetal. Now, it will be ionic, but a lot of times it'll be very close to what they'll say as a polar covalent. but it is still going to be an ionic compound.
So is a covalent bond just like a bond between a metal and a metal, or a non-metal and a non-metal?
Non-metal, non-metal. Metallic bonding would be metal and metal, metal, non-metal, ionic, and two non-metals, covalent. Now, during the year, especially when we covered this, I'm not gonna lie, I got a little frustrated at this part because the number one answer that I got for why is there a difference between anything, it was always shielding. That's not true, okay? All right, now, in general, we said the left to right, it increases. The reasoning behind. We're dealing with, if I'm dealing with, where's my marker? Parker, where's my marker? There we go. If I'm dealing with two elements in the same period, if they're in the same period, what does that mean is also the same? If they're both in the third, Energy levels. If I'm dealing with two elements in the third period, whether it's sodium on this end and chlorine on the other end, they're both in the same period, which means the electrons I'm dealing with are still in the same energy level. Would shielding have anything to do with two atoms in the same energy, two sets of electrons in the same energy level? No. In order to be a shield, you have to have something between. There has to be that difference. If they're in the same energy level, there's nothing to shield. Yes?
Why do you put the thing with the bigger next to the N?
What?
Oh, that's A.
Yes. All right. So, when it comes to dealing with two elements in the same group, the same period, in the same period, that's what we looked at. Coulomb's law and repulsion. Coulomb's law more so than repulsion, though. Now, what is Coulomb's law telling us? Coulomb charges. What is Coulomb's law telling us? Has something to do with the amount of charges. What? It does have to do with attraction. You said the what? The higher the magnitude of charge, the more attraction you're going to see. So, if I were to ask you to justify or to explain, why does chlorine have a higher ionization energy than sodium? The first place I'm looking is, what is the nuclear charge? For chlorine, it's 17 versus sodium, it's 11. Chlorine has more protons, which is going to give it a larger magnitude of charge, which is going to cause more attraction. If it went the other way, why does sodium have a smaller ionization energy than chlorine? Same idea. Welcome. Now, if it's, again, in the same group, Coulomb. Now, in the same period, Coulomb. Now, what about if I'm dealing with in different periods, same group? So if instead I'm looking at fluorine versus bromine. What's now going to be my difference? This is where shielding is going to come in. Now, this is in period 2. Period 2. This is in period 5. So if I'm looking at these two, it's not enough just to say fluorine has a higher ionization energy because of shielding. What is shielding? What does it mean to have a shield? To block something. What's doing the blocking in this case? What's in the energy levels that's doing the blocking? Electrons. So, I would identify, this one is in N equals 2, versus this one is in n equals 5. N, of course, in this case being our energy levels. And I point out the fact that with the increase or the difference in energy levels, that also increases distance and the number of electrons between these two atoms, or between the nucleus and the electrons. That's what's going to help me to see, oh, this is what shielding actually is. It's not just saying everything is shielding, which is what I got on the FRQs at that point. Okay? I'm looking at what causes the shielding. That's where the repulsion is going to come in. That distance between the nucleus and the valence energy shells or whatever we're dealing with at that point is what's going to cause that shielding.
No.
What about the protons?
They cause the nuclear charge.
That was what we were telling me.
Can we change the protons?
You change the element. Now, I feel like that's going to be a question that's asked at every single one, and somebody's going to be watching the video and be like, why do they keep asking about the protons? Okay,
What do you mean a video?
I'm recording this now.
Right now?
Oh, God.
They're hearing your voice.
Follow me on Instagram.
Everybody say hi. Nah, it's not that deep. All right. Now, this was the
Your best friend.
second part that we just talked about, the shielding, the electrons being removed on average further from the nucleus. Now, the fun part, the exceptions.
Hey.
The exceptions part goes back to structure. All the issues that we see with the exceptions. Why is it that despite oxygen being further over, it has a lower ionization energy than nitrogen? That goes back to the arrangement of the electrons. I'm going to throw some at you. Each time you see one of those little dips, one of the things you're going to start to notice, or you should start to notice, it's about at the same point in each period. Okay? So between nitrogen and oxygen, phosphorus and sulfur, then we introduce our d orbitals, and then we get these two are about the same, and so forth. It's all based on how much the orbital is filled at that point and how much repulsion between the electrons. Questions, issues, concerns? If I was to, yes.
It's because the noble gases are more stable, right?
Because they're more stable, they lose more energy, meaning it would take more energy to pull them, yes.
Okay.
I wasn't sure if you were asking in regards to the exceptions, though. Or that was just in general.
That's just what,
Okay.
What about the exceptions? What is that?
Nitrogen, oxygen, notice that we have a trend going upward, but here we have a change where beryllium is higher in energy than boron, nitrogen is higher than oxygen, and it has to do with the filling of the orbitals. If I have a full orbital, it's more a full or a half-filled orbital, especially when p and d orbitals, they're more stable than having to go beyond that, and that extra electron wanting to sort of get out of there. And another situation of showing the actual data where you can see the numbers. This is just from sodium all the way to argon. Notice how drastically these change. It is possible to remove them, but usually you're going to use something more like X-ray energy in order to do so. And that's where the PES part came in. Questions, issues, concerns? Wonderful. All right. Now, next thing we had to deal with, electron affinity. If I have an affinity towards something, it usually means that I like it. I have an affinity for cheesecake. Just a hint for future gifts. Now, if, hey, I'm good with that. Now, this is just looking at when I add on that electron, does it cause more chaos or does it release more energy in the process? If I have a metal and I add in another electron, those metals are trying to get rid of the electrons in the first place. So instead of decreasing in energy, I'm going to have a much, much higher amount of energy. This one goes, the trend is the same as ionization energy. Yeah, that's what this says. So as we move from left to right, it becomes more negative, and as we go from top to bottom, it becomes more positive. Again, dealing with the repulsions of the electrons and so forth. Questions, issues, concerns? Electron affinity really comes in when we talk about bonding. So we're going to deal with this and tie it in a little bit more than we were able to do in class when we talk about lattice energy and so forth. And atomic radius, again being the oddball of the bunch, looking at the fact that it decreases from left to right for the same reason that the other ones, the other values increase from left to right. And as we go from top to bottom, it also gets larger. The more orbitals, the larger the radius. Good? More Oreos, larger the radius. Orbitals, Oreos. Just make the connection. All right. Now, the other thing that is going to come in here, and you may see this in a test question or you may just see it in practice. The other question that may come in from this is ionic radius. How would, whoa, that's a weird word. How would everything change if I'm now looking at it in terms of the ionic radius instead? What would I expect to happen between the atomic radius of lithium and the ionic radius of lithium? I'm losing an electron. What should happen to my radius? Why? Losing electrons, which will get rid of that last energy level, making it smaller. Conversely, on the other side, what about if I add an electron to chlorine? What should I expect to happen?
Where's the strain?
Bro.
It's going to grow just a little bit. Why?
Because you're adding.
Because I'm adding that. A little bit more clarification. I am adding. Why would adding another electron to chlorine cause it to grow toxic? What am I introducing into it? Denise, with it. What do we know about electrons, guys? What's the charge on an electron, Denise? You guys are scaring me today. It's negative. If I have 7 electrons on the outer ring hanging out, and I throw an 8th one in, why would the radius get larger? What are the electrons trying to do? Tyreek. Is going to increase the repulsion between the electrons. Stop scaring me. Today I've had people ask me, how do you figure out molarity? I've had people ask me, how do you find the number of moles? And I've asked the question, what's the charge on an electron? And gotten, I don't know. That's scary. Okay? That's very, very scary. We have a lot of ground to cover. Okay. Now, chemical bonds, because this is all where we're trying to go, this is where we're trying to tie everything to. Covalent bonds, we're looking at sharing electrons. The resulting collection of atoms is then a molecule. Notice, shared electrons, molecule. Not shared electrons, not molecule. Okay? So if you look at something that says formula unit or something like that, it's ionic. Ionic bonds, we should know these 3 big terms. An ion just has a negative, positive or negative charge. The positive version, a cation ion. Older people tend to think cats are positive. And anion, negative. Onion breath is negative. Anion sounds like onion.
It's an onion.
Workings. Sure. Now, when we deal with ionic bonds, the only thing holding them together, it scares me when I hear people respond. Only thing holding them together, there's no sharing of electrons, it's just the opposite charges. I keep repeating things like this because, again, I keep getting scared. People give answers and they worry me. Periodic table, metals versus nonmetals. We should know this part. This was Red Chem or Honors Chem for you guys. Yeah. as well as where the groups are located. Now, I have a question. Why are the alkali metals the most reactive metals based on what we know about the structure of the atoms in that group? Rajiv, why are these the most reactive metals out of the entire periodic table based on what we know about the structure of the atom?
Is it because they don't satisfy the integrity?
That is true. Why would that apply? Would you like to phone a friend? Who's your friend? Grace, go ahead.
Is it because they only have that one electron at a time to use to get to their nuclear gas structure type thing? So they're trying to like react with everything to get rid of that electron.
Correct. In each case, they're willing to be oxidized in order to lose that electron and have the electron configuration of a noble gas. Look on the other end of the periodic table. Why are the halogens the most reactive nonmetals? Nasa. Why are the halogens the most reactive nonmetals?
They're closest to the nucleus?
They're closest to the nucleus?
No.
I think the term you're looking for, it does start with an N.
Oh, I know.
It's on the screen, man.
The noble gas.
And why would that make them more reactive, being that close to the noble gases? Why? I'll allow you to tag somebody for the next part.
Maya. You ain't got no friends, so.
Maya, she's already given us that they're sitting right next to the noble gases. My question is, why would that make them so reactive?
Because they're friends.
Don't scare me. Taylor, they only need one more electron in order to fill their octet. Now, the questions that I just asked, again, if you don't use information, you lose it, right? The two questions that I just asked are honors chem questions. They were not AP level questions. It's just understanding basic structure, okay? Where things are placed. Another trend that doesn't come up much, but every once in a while they throw it on. Metallic character. Metallic character. How much of a metal is the atom that you're dealing with? I'm going to give you a hint. What do you think happens to metallic character as you go from left to right?
Decrease.
Why decrease?
Because metals are on the left. And gases are on the right.
Correct. Hold on. Without applying much chemical knowledge, that was a logic-based question. If I already know that metals are on the left, non-metals are on the right, the metallic character has to decrease from this way. What about from top to bottom? What about from top to bottom? Within the group, what happens to metallic character? Correct, it decreases. As it goes from here to here, it actually decreases. The structures, the easiest way to put it is this. As you move this way, it's applying the entire trend, you notice that you become more and more non-metal. Same idea is happening here. Okay? So, as you go from here to here, you may have more of a metallic character here. It's not really much of anything, but more of a metallic character at the top than you do at the bottom.
Then can you explain what that is?
Metallic character is like, if I was trying to figure out, I don't want to say it. If I was trying to figure out how different metals would react in terms of forming alloys. I might look at metallic character. Okay? It's looking at how I can get those two metals to react together, or not react, to mix together to make something stronger, or to allow their properties to overlap so that it makes something stronger. Like putting iron with a definite non-metal, doesn't have much of any metallic character, carbon, make carbon steel. In putting those two things together, one, it works together because the radius is that much smaller, but two, the properties and the strength that come from carbon by itself enhance the steel, enhance the iron to make it that much stronger. What type of alloy would that be if I was looking at carbon steel? We had two. We had interstitial and substitutional. Would it be interstitial or substitutional alloy if I'm looking at carbon steel? Between. Between. That's literally what it means.
It's like inside of
Yeah, it's like everything is there, you just pack these between. Whereas substitutional will be
the.
in place of. Yeah. So carbon steel, definitely interstitial. I think we know that part. I don't even know why I forgot to erase that one. But the basic groups you should know, if you hear alkali metals, any of these four basics, you definitely should know where things are. Now, naming compounds, we know this, but I'm going to review it because, again, people scare me. Binary ionic or binary compounds in general, we just have two elements. That can be ionic or covalent. Ionic compounds, metal with a nonmetal. Remember I-heart bonding, metal and nonmetal, ionic bonding. We wrote that on the board, told you to write on your paper. And covalent, binary covalent, which is what we deal with on the regular, will be the two nonmetals together sharing electrons. As far as the basics of naming, always name it first, name the metal first, the anion second. Common mistake that comes in here, and I think it's shown here, there we go, is with our transition metals. Please do not forget to put in those extra charges. That will annoy you and mess you up on future net ionic equations. And because you'll use that information later, it will come back to bite you. So examples, so forth, make sure you can balance the charges. Hey, Anthony. I'm doing review session for AP.
Okay.
Yeah. Mondays and Fridays. Yep. Mm-hmm. Polyatomics, you need to know them. You need to know them. Those who are like, but that's a long list. Yeah, but they tend to be repetitive in the ones that they use. So, if you know a good portion of them, the ones I told you, nitrates, nitrites, when it changes to those and so forth, you'll be fine. Questions, issues, concerns? Good? Wonderful? Great. Ditri, you should know those. The naming stuff should be pretty self-explanatory. All right, last couple things, because we're actually almost at the end of this one, which will conclude Big Idea 1. And then we can look at a couple of questions. When you're dealing with carbon chains in general, this is one that we haven't really covered a lot in class and talked about. If you look at some of this ethane, propane, propanoic acid, whatever the case may be, these are the prefixes that you're actually working with. Meth is just saying 1, F, 2, prop, 3, so forth. You may want to write those down, record them somewhere, because they will come back to bite you. They don't like to say acetic acid anymore. They don't say vinegar. They say ethanoic acid. As soon as you see that F part, you should know 2 carbons involved and start to piece together how the formula will look. I'm assuming you're taking a picture. Okay. Also, and I don't think I put it on the slide, if it is an alkane, meaning it contains all single bonds. Was I in the middle of that? Okay. If it's an alkane, contains all single bonds. The formula for writing it, just in case you're trying to figure out how many hydrogens, is going to be CnH2n plus 2. So, if I'm looking at ethane, that's why it's C2H6. I have my 2 here. 2 times 2, which will give me 4 plus another 2, is an easy way to figure it out. If it's an alkene, yes, there is a difference between them, and yes, they just change those few little parts. That means it has at least 1 double bond. Notice it doesn't have to be all double bonds. It's just, it includes 1. Which means you're not going to find a methane. That doesn't exist because you have to have at least another carbon. Then it's going to be CnH2n. And last but not least, alkyne. Alkyne. At least 1 triple. And that one is CnHn. Now, question. If I'm dealing with hydrocarbons, why do you think when I have, I don't know, ethene, why would I have to follow this pattern, CnH2n? What dictates the amount of bonds I'm able to form? This is similar to one that was on your mock. What dictates the number of bonds I'm able to form? How many hydrogens I'm able to attach? The amount of electrons. So if I have ethene, I automatically know that I have a double bond that's in the midst. I know that carbon has 2 more valence electrons on each if it's already sharing these pair. Just that simple. Just to throw these in there because you're going to need them. And I probably should have hooked up my thing on here so I could have written them on screen. A couple of basic, very, very basic functional groups that you need to know. I'll write them on this side since it seems a little bit easier. Everybody's good here?
No. What's the thing next to all symbol?
Alkane? Alkane, alkene, alkyne. Only thing that changes goes from A to E to Y.
What?
We're good?
No, we're not.
Okay, we're good? All right. Functional groups, basic functional groups that you'll need to know. Functional groups are basically add-ons to this. So if I had CH3OH, that OH tells me that this is an alcohol. So it would be or what we'll say is a hydroxyl group. If it was just OH by itself, with a -1 sign, it's a hydroxide. If it's attached to something, as in a covalent compound, it's a hydroxyl group. Same thing for each of these. If I was going to put in the CH3, it would be a methyl group, an ethyl group, propyl group, and so forth. Yes?
Will we get a question on how to name what you just said on the quiz?
What they tend to do more often is they throw it into a Lewis structure question. And they'll ask you what's the difference in the arrangement of these two things. That's where also that term isomer, which I'm sure you've seen on both mock exams, and we talked about it very, very little in class. It just means I have 2 compounds with the same exact components, same number of carbons, hydrogens, oxygens, whatever. But the arrangement is different, and so that gives it different properties. The next one that you'll see, I already mentioned, carboxyl group or carboxylic acid. today, carboxylic acid. Oops. Next one, NH2, amine group. So when you hear that term amino acid, amine, amino, those are related. It's telling you that one of the major bonds or major components is this. Everything is built off of that. Three quick ones. Ketone. Oops, I might want to actually say what it is. C, O bond O. See, I'm drawing this one out because it's easier to see it. A ketone group. You have a carbon with a double bonded oxygen, but you have the chain continuing on both sides. An aldehyde group, which would be this. Oops, let's give some space. But there's a terminal hydrogen on one side. This would be an aldehyde, like formaldehyde, stuff that stinks and preserves dead things. And last but not least, and I think I can squeeze it in here, if I have carbon, oxygen, carbon, this is where I have an ether group. Nope, sorry, ester group. For those who like to spray on stuff that smells sweet and all those fruit and flowery smells, usually those are esters that you're smelling. This is a basic, at least a little bit of a basic into organic that you're at least where we're gonna have to go. Be able to identify what that's gonna do for each of those, for each of the compounds, sorry, and how that will change the structure just a little bit. Did that. Oh no, we didn't do that. Crap. I thought we were finished. I was hoping. Where we at? We got 12 minutes. Yeah, time moves. All right, this is one that we didn't get a chance to cover really in class, but when we look at the structure of our compounds, notice that we went from percent composition, and sort of, not percent composition, no, we did percent composition, and figured out the mass percent and so forth. See, when we deal with each of our individual elements, of course, we know that we have different isotopes. Those different isotopes have different masses due to what, Parker?
The protons.
No.
You
The isotopes have different masses based on what?
Neutron.
Different neutrons. Thank you.
Oh, you pointed at me.
I was expecting you to go other than protons.
Do you know who I am?
Yeah. I'm finding out more and more each day. A little scary. Now, if I'm taking a look at this, this is just saying that when I look at that masses on the periodic table, we know that it's made up of, and it has to represent all of the isotopes of carbon, including carbon-14, which makes up less than 1% of the naturally occurring amount. If I needed to figure out the average atomic mass, which we can easily do, mass times percent abundance, change it to a decimal, then do that for all of them, add it up. This is a weighted average. This is the same way we calculate your grades. Lovely. Now, does it say it? Okay. Now, one of the things I want you to also realize here, one question, or a couple times I've seen a question similar to this, where they ask, which compound or which isotope do you think is more abundant? If I'm looking at carbon overall, looking at the average atomic mass that's given for it, could I easily predict, without the percentages, which isotope is more abundant? How? Look at the mass. If it's a weighted average based on how much of each I have occurring naturally, the mass is 12.01. I know that 13 isn't really making a difference, nor is 14. So the one with the highest relative abundance, or the one we find most in nature, would be our carbon-12, which is what everything is based off of. This stoichiometric, we rounded, it tells you that. Now, this is how we figure out that information, which leads us to our percent composition type deal. Use what's called a mass spectrometer. This nice device takes a sample, shoots it in, and accelerates the beam after stripping away some of the electrons. As we separate them out, we're able to get the mass, the higher mass, down here, smaller mass towards the top. That part should make sense. Heavy stuff falls, light stuff rises. Makes sense. It's going to be detected on that plate, and you get a nice data plot of a bunch of peaks. From that, you can determine, hey, we have this much of this one, this much of the next, and so forth. Yes, they will ask questions possibly about a mass spectrometer, how it works, or just give you a plot of the data. And you just have to figure out what the average atomic mass would be. We use that information. Since if we're dealing with pure carbon-12, we can use that to figure out how many atoms were in 1 mole of carbon, and that's where we got the 12.01 grams. See it, Benji? So this number was not just some abstract thing that somebody came up with. They actually did experiments and calculations. When it comes to mass percent, this was one that you would have seen on your mock exam. It asked about the mass percent of a compound. The mass of the element in the compound over the overall mass in the compound sounds very similar to percent composition. The difference is, and this is the mistake that a lot of people tend to make, they'll look at it and just put the mass of one iron for whatever not so bright reason, or they didn't figure out that, hey, even though I'm not dealing with a full mole, I still have to consider the ratio at which they're mixed. So if these numbers were smaller and I was, instead of dealing with a mole, dealing with 0.05 moles of it, I have to make sure that my values are adjusted accordingly to figure out the percentage. Once I've done that, everything becomes like a percent composition style problem. Empirical formula, you guys should know that, simplest whole number ratio. And we can figure it out from the amount of water and carbon dioxide if we're dealing with hydrocarbon. Why? What law makes it so that we can figure that out? What's the only law we've really talked about so far? Everyone's favorite one. Law of conservation of mass. If I know how much carbon and hydrogen I produce at the end, I can easily work backwards to figure out what the composition of my compound was at the beginning. Hasta luego. Have a good one.